Hello students, welcome to this lecture number 18. In this lecture we are going to discuss a very important thing, that is the electronic configuration of the atoms of the element. And this will be the 18th lecture, and it will be the last lecture of this structure of the atom chapter. In this chapter, we will going to learn how we can able to write the electronic configurations of the atom. So we can write the heading of this lecture is electronic configuration. Electronic configuration of atom, because we already know the atoms is been composed of different numbers of electrons. So this is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Electronic configuration. What do we mean by the electronic configuration? Let us first understand. Electronic configuration means the arrangement of the electrons in the atoms and in the various orbitals. How the electrons in the atoms has been arranged. Basically, if we know the rules governing this filling of the atomic orbitals in the atoms, if you know this, so you can easily able to write this electronic configuration of any atom if you know its atomic number. And we know in the previous lecture, that is lecture number 17, what are the rules which is going to govern the electronic configuration filling of the electrons in the orbitals. There are basically two ways that you can able to write the electronic configuration of the electron. Number one way is, that is, in this way you can write this is called the subcell. These are all basically the subcell. S subcell, P subcell, D subcell. And in that subcell there is a superscript, and this superscript is represented, is being denoted the number of electrons that is present in that particular subcells. So this is subcell, and the superscript, that is A, B, C, denotes the number of electrons in that subcell. And to differentiate the same subcell in that cell, that you have to put the principal quantum number of that cell. Suppose if it is in the cell number 1, so you have to give the principal quantum number of that cell number 1 means 1. If it is cell number 2, this is 2. Likewise, you have to put the numbers 1, 2, 3 in the left hand side of this subcell. So let us understand how this subcell notation been followed while writing the electronic configuration. We know the hydrogen is the most simplest element, and it is having the atomic number is 1. So this electron, how this electron will be arranged in the orbitals of the hydrogen? Naturally, above principle says the electron will be filled in order of increasing the energy of the orbitals, and it will be filled in the lowest energy of the orbital. So we can write this 1 is 1, means this one electron will be filled in the S subcell, and this is the principal quantum number is 1, and in that subcell this electron will be put in that s orbital. We can see that this is s subshell. In the s subshell, the one electron will be put, and this number of the subshell present in the principal quantum number, that is 1. So we can write this 1 is 1. So next element, that is helium. You can give 2, and it is given the 1s2. We know that any orbitals, that is the Pauli's exclusion principle, any orbitals can accommodate only 2 electrons. So there is a space available for this. So in the 1s orbital, you have to put the another electrons, that is second electrons in the helium element. Next, that is lithium. Lithium, we know it is having the atomic number 3, and it is being, you see the 1s orbital in the subshell, that is the electron has been filled, because the capacity of this orbital is only 2, and in the one cell, that will be only one subshell, that is 1s. So this number 3 electron, that will be filled in the next energy level available, that is the next orbital, that is 2s1. So in the lithium, you can see that is 1s2, 2s1. That's 3 electron has been arranged in this fashion. First 2 electrons will be in the 1s orbital, and then last electron, that is the number 1 electron, that is this electron, will be put in the 2s orbital. Then the next element, we know that beryllium. Beryllium, as the atomic number is 4, so its electronic configuration will be like this: 1s2, 2s2. So this second electron will be put in the 2s orbitals. That is the electronic configuration of the beryllium. That the 4 electrons the beryllium will be arranged in this fashion. That is, the 2 electrons will be in the 1s orbital, another 2 electrons will be the 2s orbital. Then it is having the boron. Boron, that having the atomic number is 5. So here you can see 2s orbital has been filled. So it will go to the next available orbitals, next available subshell. Next available subshell is 2p. So we can write 1s2, 2s2, 2p, and this 2p, 1, there will be only 1 electron will be filled. Then after boron, there is a very important element, that is carbon. Carbon having the atomic number is 6. So it will have 1s2, 2s2, 2p2. This is 1, 2, 3, 6 electrons. Then you have the next element, that is the nitrogen. Nitrogen having the atomic number 7, and it will have the 1s2, 2s2, and 2p3. In this fashion, you can see the electronic configuration of the elements has been done as per this notation. This is the subshell notations. This is another notation that will be side by side, we will understand, that is the orbital diagram. Orbital diagram. In this orbital diagram, you can see, you can observe that the orbitals in the subshells. Orbital in the subshells has been represented by the square. So you can see, suppose this is the A subshell, this is the P subshell. In the A subshell, we know there is the only one orbitals, that will be represented by this. In the P subshell, that will be 3 orbitals and will be represented by this square. So orbitals, in the orbital diagram, it is represented by square. Every orbitals in the subcell has been represented by square, and as the S subcell having the only one orbital, that is only one square, in the P subcell, that is three orbitals, that is given by the 3 square. So now we understand for this electronic configuration of hydrogen, this can be put here. And here another thing that we need to understand, that is the electron. How we put the electron, that is again another thing. We put the electron in this fashion, that is this arrow, the upward arrow, and sometimes when the second electron will be in the same orbital, we have to give the downward arrow that will represent the positive spin or the negative spin. So in the orbital diagram, we can represent the hydrogen is like this way, that is only one electron. Helium, we can see that, you can see that is two electrons are put here in the 1s orbital. This is basically, you can see, this is 1s orbital. In the 1s orbital, in the helium, you can see the two electrons. In the lithium, you can see this is 1s orbital filled. Then you have to go the next orbital, that is 2s orbital. This is 2s orbital, you can see 2s orbital. In the 2s orbital, the next electron will be put. So it is having the 3 electrons that has been arranged in this way. In case of beryllium, it will be this. In case of boron, this will be this. So you can see the electrons has been put in the different square, which is representing the orbitals in the subcell. In the beryllium, we have already done, and this is boron, and in the 5, these 5 electrons have been put in this fashion, 2 electrons, 2 each in the 1s and 2s, and another electrons that is put in the 2p orbital. This. For the carbon, this will be for the nitrogen, you can see in this way, you can put 3 electrons in the 3 2p orbitals. So this is how you can represent these electronic configurations in different ways. In first way, that is SPD notations, there is subcell notations. Then second way, that is the orbital diagrams. In the orbital diagram, you can see the electron has been put in that orbitals, which is represented by a square, and the electrons is been put in this has been as a arrow, that is upward arrow, and here it is a downward arrow, because we know the electron, that is the Pauli's exclusion principle, that no 2 electrons will have the same 4 quantum numbers, and that is why when the pairing with the electrons in the same orbital will be done, and then that will be the oppositely spin. These two way of representing, two way of writing the electronic configurations of the atoms that we understand, that is the SPDF notation, subcell notations, and in that subcell there will be the electrons, how many electrons is present, that will we have to write. And the second notation, orbital diagrams, in that case the orbital has been represented by a square and the electron is represented by the arrow, upward arrow or downward arrow. What is the difference between these two representations? Is there any difference that you can think? What is the difference between these two orbitals? Is there any difference? Yes, there is a difference. You are right, that because in the first notation, SPDF notations, there are only the 3 quantum numbers of the electron has been represented. That is your, which is the, in which cell the electron present, in which subcell it is present, and having in the which orbitals it is present. That is the magnetic principal quantum number, azimuthal quantum number, and the magnetic quantum number. But in the second notation, and fourth quantum number is represented, that is the spin quantum number, by giving the arrow of different arrow, that is the upward arrow, downward arrow. In this fashion you can see that is why this the fourth quantum number is represented in the second notations, where in the first notation there is only 3 quantum numbers of the electrons has been represented. So this is how you can see the difference of both the notations. Then we will again write the different electronic configurations of different elements, like we have then you have sodium. Sodium, we know it is having the atomic number is 11, so its electronic configuration will be 1s2, 2s2, 2p6. Before sodium, that is okay, we have already covered up to nitrogen. Then after the nitrogen, this is oxygen. Oxygen having 8, and it is having the electronic configuration 1s2, 2s2, 2p4. Then after oxygen, the next element is fluorine. It is having the electronic configuration is 1s2, 2s2, 2p5. And after that, the neon, it is having the electronic configuration have 1s2, 2s2, 2p6. So in this cell, in that neon is basically a noble gas. You can see every subcells available, every orbitals available in those subcell has been filled. So it is having the totally filled orbitals. And the next element, that is sodium 11, that is electronic configuration will be 1s2, 2s2, 2p6, 3s1. And in this fashion, we can able to write the electronic configurations of the other elements also. Here you can see that this electronic configuration can be simplified. How? That this is the electronic configuration of the neon, right? So we can rewrite this electronic configuration like this, that is Ne into 3s1. Now there is a two concept we need to understand. One, that is the core electron, core electron. What is the core electron? Core electron here this is the core electrons where the totally filled orbitals has been totally filled. This will be the core electrons. You can see in this case neon core electrons in this atom, that is sodium atom, core electrons is only 8, because these electrons are the inner electrons and it is completely filled, and the one, that is the electron in the highest valence shell, electron in the highest valence shell, it is called the valence electron, electron in highest energy cell, that is the highest energy cell, that is the valence electron. Here valence electrons is, you can see it is 1 for sodium, it is 1. So you can understand this core electrons means in an atom there will be a core electrons and other will be the valence electrons. In this case sodium, core electrons is, number of core electrons is 8, because all the electrons, all the orbitals available at the core of the atom has been filled by the electrons. So this is core electrons and this is the valence electron. And valence electron is the most important part of an atom because it is going to take part in the chemical reactions. So you can see from sodium, that is 11, and this goes up to, you can see, that is argon. Argon having the atomic numbers is 18. So this can be written as 1s2, 2s2, 2p6, 3s2, 3p6. So this is the electronic configuration of this. So next element here is, we know, potassium. Potassium is having 19. So we can write this electronic configuration with argon. Name the core electrons we are not going to represent here. We are representing the element which is having these core electrons. The electronic configuration of this element, that is, it is basically, you can see this is the argon, and after this we can write the 4s1. One thing you can see that 4s1 in the potassium, the 4s orbital filled, but 3d orbital has not been filled, because of the fact that 3d orbitals having the higher energy than the 4s orbitals, that we know as per above principle that energy will be filled in order of increasing their energy. So we can apply here above principle. So after this is another element, calcium 20, and it is having, you can write this way, electronic configuration 4s2. After this there is another set of elements started, that is scandium, titanium, vanadium, chromium, etc. That is all we can learn in your periodic table, and this is the 3D transition element, and you can go through my video, that is in the periodic table, and you can understand this, how this has been arranged in the periodic table. So this is the next will be the scandium 3D periodic table, and it will go up to the krypton. In this way you can see that you can able to write the electronic configurations. And there are some element electronic configuration you will found that is different. As for example, chromium having the atomic number is this. So we will write this electronic configuration like this way: 1s2, 2s2, 2p6, then 3s1, 3s2, 3p6, then 4s, then 3d. After filling of these 4s2, then 3d orbitals will be filled, and in the 3d orbital you will find there is this. If we go, this is, you can see number of electrons 10, 12, 18, 22 and this. If you go by the above principle, you can principle and others electronic rules for the electronic configuration, this will be the as per this practice. But this is not true. The electronic configuration, this is not true. This is not the correct electronic configuration. The correct will be this. This will be the correct, because this electronic configuration is much stable. As per Hund's rule, the halfly filled or fully filled orbitals will be, electronic configuration of the orbitals will be highly stable, because of there is two reasons, that is the exchange energy and the number of energy, that is the energy will be available will be higher, that this will stabilize the energy of the electrons, and this will having, due to this fact, this will having this the highest energy, and this electronic configuration will be preferable. So that is all for today's video. In this today's lecture, we have discussed about the electronic configurations of the atoms and some exceptions also. And we also understand that halfly filled and fully filled orbitals are the most stable electronic configurations. And that is why you can see the chromium having that different electronic configurations. That is all for today's video. If you like this video, you can share with your friends. Thank you very much for watching. All the best.